upon I repeat it a few times, okay, in order to really, give you some impact and understanding about that. All right. A few things to clarify as well. Okay, so I supposed to have the same at the moment. Actually, I am in Johor. I'm going to attend a meeting this afternoon. Okay, physical face to face. In Marsa College. So I'm very sorry because for the KSF2, I might be able to be with you all online like this. Okay. But I'm supposed somebody will please do the recording, okay, so that those who cannot join this group from KSF2, hopefully they can see and they can just go through the recording. Can somebody record the meeting now? And that's the first thing. Okay, so but the attendant will be there. So for KSF2, okay, please record your attendance. Your attendance is not available at the moment. Okay, your attendance will be available at 2 o'clock. Okay, so those who already for KSF2 who already joined this group, please record your attendance. Okay, 2 o'clock onwards. Okay, until 4 o'clock. Okay. And then secondly, okay, regarding the tutorial that I supposed to do last week, and I think most of you prefer to have it tomorrow. Okay, tomorrow actually I'm on my traveling back. Okay, to Nilai. Okay, to Nilai. But I simplify basically the tutorial. Okay, and hope today some of the material. Okay, we're going to discuss today. Okay, so hopefully you will get some clue. Okay, so for tomorrow, basically there will be no face-to-face. Okay, so I'm going to give you 1 week. Okay, basically, I'm going to upload the tutorial. Okay, the tutorial question in assignment icon. In the MS Team. And then I want you to submit according to your group. Your group will remain is the same group as what you are. For the same group as for the for the practical. Okay, so maintain the same group. Much easier for me to follow. Okay. All right. Question about the tutorial. So and then what else? Okay. The lecture for this for this NMR comprising two subtopic. Okay, if you like. Last week we discussed about the concept. Okay, we discussed about the concept. What is NMR? Okay, more or less. Okay, so and that concept applied for both. Okay, for a proton NMR as well as for carbon-13. All right. So today we're going to focus. Okay, since we already done with the principle of NMR last week. The instrumentation, okay, more or less, and how the what you call it, the signal being generated. So today we're going to focus on the chemical shift and also the splitting. Okay, the chemical shift and the splitting. What make the shifting in the signal, and what make the spin split. Okay, and producing doublet, triplet, quartet. Okay, and so on. Okay. All right. And at the same time, because I'm afraid we might not have enough time, to go detail into carbon-13. Okay. But as I said, the principle is the same. So I already did the pre-recorded lecture. Okay. So basically, I record my own lecture, on the carbon-13. I think you can find that, in MS Team as well. Plus, there's one video that I attached, on the carbon-13. Okay, one video on the carbon-13. Thank you, Soraya. Okay, on the carbon-13. Okay, videos that we need to go through. Jadi untuk carbon-13 ni, anda supposedly I had maybe not having enough time today, or maybe you put a bit blur, for instance. Just go through my pre-recorded lecture notes. Plus the video, you should be able to grasp. All right, and I think this also required in order for you to do the tutorial. Okay, because the tutorial actually I just give you very simple question based on a past years punya question. I just compile saja. Okay, past year question, then see whether you can answer that. Okay, so it's not really challenging. I think suitable because this is the first time that you've been introduced to spectroscopy on the carbon-13 and proton, hopefully you should be able to do that. Okay, so some example that I've been put it, in my video, in my pre-recorded lectures, as well on the videos that I attach. Okay, I think you should be able to grab the information, inshallah. Any further question you want to ask, Ananda? Silence means okay, you're okay with it. All right. So now what I'm going to see, I'm going to do. Okay, so I'm going to show one of the videos. The video actually maybe the slang. Okay, slang dia mungkin anda tak berapa familiar sangat. Mas Salih punya slang dia macam Scottish sedikit. Okay, but I noticed that the video actually is very good because it just based on a piece of material that been put in the cupboard, put in the blackboard. Okay, more or less. Okay, and then he explained the same thing based on that. Then there are a few series. Okay, they have a few series, for the carbon-13 introduction. They have, on the introduction of the NMR, and also they also having, on the introduction on the proton. Jadi complete proton NMR. I mean introduction on the principle of NMR, proton NMR, and carbon-13. Okay, tapi dia tak ada animation. Okay, dia just cakap saja. So I will show, for the carbon-13 and see if you can grab. I just going to explain that a bit. Okay, because the note is there. Okay, always in front of him. Okay, and then he doing the explanation. Because I attest, I think it's about 3. Okay, of his videos, and actually, the citation. Okay, the number of likes is quite. It's quite enormous. Okay, so maknanya explanation is very good. All right, and then we will go into the lecture notes. Okay, that we have. Okay, that I under prepared. All right. Okay, so I share the videos. I'm going to share the screen first. There you. Okay, Ananda, this is the gentleman I'm talking about. Okay, so basically, the way he worked, he put everything, the things. I mean, he already summarized everything about the NMR proton. Okay, in this the whiteboard. Okay, so everything what is going to explain is here already. Okay, and then he's going to explain, step by step. But it's not going wrong. He's not going to run away. Okay, from what he has wrote, in this whiteboard. Okay. So, but the slang, I think actually it sounds a bit Scottish, okay. But I think later on, okay, when you are, during your spare time, okay, maybe you can go through on your own, okay, and see whether you can follow. Okay, so please pay attention.
OnlyTutors.com, and in this video we're going to be looking at proton NMR. Now this video is just going to look at a very simple overview of proton NMR, and there's going to be no mention of splitting in this video or spin-spin coupling reactions. So if it's that aspect that you'd like to look at in terms of proton NMR, then you just click on the link below and you can see that video there. Like I say, we're just going to keep this one relatively simple. So what we've got is we are effectively going to look at 2 molecules, and we're going to assign the different hydrogen environments to NMR spectra. We're also going to look at what we mean by peaks, chemical shift, integration as well. We're also going to look at the solvents that we use, and you may have heard of the Harlem shake. Well, in chemistry, we've got the D2O shake, so we're going to have a look at some of that as well. So if we just start off with our 2 different molecules here. Now, we're looking at proton NMR. So as opposed to carbon-13 NMR, where we're looking for carbon environments, and this one, we're looking for proton environments instead. So we're looking at the hydrogens in the molecule. The principle is the same, though. It's exactly the same as carbon-13. So we've got a few points that I want to make you aware of here. And this is about the number of peaks in an NMR spectrum. Basically, the number of them tell us how many hydrogen environments we have, and I'm going to work through and show you how we can assign these peaks as well. We're also going to look at something called chemical shift, and again, just like carbon-13 NMR, if you've done that, this tells us the type of hydrogen, what environment the hydrogen's in. So, for example, if it's bonded next to an oxygen or a nitrogen, etc. So, and you'll get a table in your exam as well that will show you the chemical shifts for different functional groups in a molecule as well. So, useful if you have that to hand, and then you can see how it relates to my spectrum here. And also integration as well. So you'll see this quite a lot, especially in proton NMR. And integration tells us how many hydrogens we have in that environment. And again, I'll go through each three of them as well when we go through these examples here. Now, as we go through these, basically, I'm just going to show you a molecule. I'm going to assign it to the peak. In reality, you're more likely to get in the exam is a spectra or set of data, and you're expected to identify the molecule from that. So we call that interpreting spectra. So there is going to be videos on there. There's a load of videos on there, sorry, that show you how to interpret the spectra and piece together a molecule. And for this purpose, like I say, it's going to be introductory to make sure that you understand it first. So we're going to start with this one here. So this is methanol, and we're going to look for the environments first. So we're going to do this in a different color to show. We've got the spectra here, and I've got the numbers. You can see the numbers show us the integration. You'll see this. Sometimes you might see it as like an S shape on the actual NMR spectra, and you'll see a number above it. And that number tells us the integration, or in other words, how many hydrogens are in that environment. So that can help us out quite a lot. Obviously, you can see here, it's more simple for this than it is for this one over here. But if we have a look, we'll try and identify our environments first. You can see we've got two peaks, so this tells us that we have two environments, obviously, in this molecule. So you can see that we've got a proton here. This is one environment, and a proton that's bonded to an oxygen directly, for example, in an OH, has its own environment. And so this one is just got a value of 1. There's one hydrogen in that environment, obviously, because it's just that on its own. And if we look at our chemical shift, if we look at our table, you will see that the OH group should come at about just over 4 ppm, which is the shift pattern. So we know that for definite, this proton is causing this peak down here, which has got an integration of 1. And you can see we've also got 3 other hydrogens that are left. Now, these hydrogens are all bonded to the same carbon. So we say that in NMR terms, they're in the same environment. So I'm going to go through these in a different color. We're going to do them in green. So if I circle these hydrogens here, these ones are all in the same environment. So NMR sees them as 1 peak, because that's the environment that we've got. They're all bonded to the same carbon. We have a chemical shift. So if we look on our table for NMR data, then we can see that this one should come out around about the 3 mark, or just above 3. And so this tells us we have a CH3, and also it's the only peak that's left in this molecule. So these hydrogens cause this peak here with an integration of 3, which tells us that we have 3 hydrogens in this environment. That's what the integration tells us. Okay, so let's look at a bit more complex example where we've got a few more peaks. We've got this molecule here. Again, there's a bit of symmetry here, and we've still got an alcohol in there as well. So you can have a look at the molecule. The first thing we'll do is we've got a hydrogen there. So straight away, we're looking for 1 peak, and we'll do this one in green. So we're looking for something with an integration of 1, because there's no other hydrogens on there that are on their own. So this is the only peak that's got an integration of 1. It's shifted quite high up as well, which tells us that this hydrogen is bonded to something quite electronegative. So this, for example, this is the oxygen. So I'm just going to draw an arrow down there, and there we go. That's that peak there. And then if we look at our next hydrogens, let's look at the next one along. We can see we've got a CH2 here. So we're looking for something with an integration of 2. Now the problem is we've got 2 peaks with an integration of 2 here. And this is because we've got this one and we've got this CH2 here. So what we have to do is we have to look at this, and you can see that this CH2 is closest to the oxygen compared to this CH2. Now, any hydrogens which are close to something electronegative, like an oxygen, will have a higher shift, what we call a chemical shift, than something that is further away. So we could say that these hydrogens here will probably caused by, will give us that peak there, because this is the integration of 2 peak, which is shifted furthest up. And if we look obviously at the next one, so we'll do this one in blue. So these bunch of hydrogens here, these ones would represent this peak here, which is the one slightly shifted. They're very close to each other, but it's not shifted as much because it's slightly further away from that oxygen. Integration of 2 because we've got 2 hydrogens. Now you can see we've already got one more peak left, and this is an integration of 9. So what this is telling us is that we have 9 hydrogen environments. 9 hydrogens in one environment. So to get that, you really need a lot of hydrogens bonded to carbons, which are bonded to the same carbon. So if we have a look here, so we'll do this one in purple. And you can see we've got a carbon here. This carbon doesn't have any protons on it, so this won't be detected by the NMR machine. But if you look what's coming from it, we've got 3 CH3 groups, and they're all bonded to the same carbon. So NMR sees that as the same environment. It's just one environment. But effectively, we've got 3 hydrogens there, 3 hydrogens there, and 3 hydrogens there. That's a total of 9 hydrogens. So if I put a loop around all of these, just like that, you can see that we've got 9 hydrogens there, and obviously this has got to be because of this large peak here. You can see that this one is a lot further away from the oxygen, so therefore isn't shifted as far. So therefore it appears at about the 3 mark roughly. And you can see again, we have a peak at 0. This is because of tetramethylsilane. If you're not sure on what tetramethylsilane is, there is a video on carbon 13 that you can look at. So just click on the link below and you can find out what TMS is and why it's used. Okay, just the last things really is when you dissolve in these, some of these, if you have a solid, for example, a solid organic compound, you can't put a solid organic compound into an NMR machine. It has to be dissolved in a solvent to make it into a solution. And so what we have to do is we have to use a solvent that obviously doesn't contain any hydrogens in it. Because if the solvent, for example, water, if we dissolved it in water, it has hydrogens in, the NMR machine, the proton NMR machine, would pick up the protons in the water, and you'd get peaks for that as well, which would give you extra peaks which are not directly linked with the molecule that you want to know about. So what we have to do is we mix it with a something called a deuterium, which is just an isotope of hydrogen. And it's basically an even numbered nuclei, so therefore the NMR machine will not pick up because it has an even number of nuclei, even number nuclei in it. So we use deuterated solvents instead. So something like you might use D2O, for example, instead of H2O. And because it's got even numbers, again, it doesn't pick it up in the NMR machine. You can use like CCl4 again. This is effectively it's polar, so it means it will allow something to dissolve. But you can see there's no hydrogens in there, so that's fine. That's a good solvent to use for proton NMR. And the last one, like I say, in chemistry, we've got something called a D2O shake. And this is useful for when we want to detect NH or OH groups in our molecule. And effectively, if we take our molecules, so say, for example, if we take this molecule here, which is methanol, and if we mix in some D2O, which is also known as heavy water, because it's got deuterium, D stands for deuterium, which is just an isotope, heavier isotope of hydrogen. If we mix it with this, effectively, we get something called a proton exchange. And this proton will drop off and it will exchange for a deuterium on there. And because deuterium is an even numbered nuclei, the NMR machine will not detect it. And crucially, because the NMR machine won't detect it because we've swapped the hydrogen for a deuterium, then this peak will disappear. So if we run the spectra without the D2O, just this, we should see this peak here. And then if we mix the D2O with this and then run it through the NMR machine again, this peak should disappear. And if it does, that's proof that we've either got an OH group or an NH group. And that's something to look out for as well in your NMR spectra. Just something worth noting as well. But that's it. Hope that helps. Bye.
Okay, another, as I said, it's quite simple the way he explained, because everything actually in one page, okay, one page here. And actually the point that he going to explain is like this, it's been listed here, okay, and just explain, I mean, he explained it nicely, and briefly as well, So for instance, number of peaks, okay, you can see here, number of peaks, okay, 2 peaks here, and then we have 4 peaks here. The number of peaks is actually equivalent to number of hydrogen environment. So as what he explained just now, okay, we have one environment here, the red one, with another environment of hydrogen here. So the number of environment, okay, that been experienced in that particular molecule, okay, will be detected, okay, will be recorded, okay, in this NMR spectrum, okay, of proton NMR proton spectrum. So similarly here, we can see that more or less we are having 1, 2, 3, and 4 groups of hydrogen. So meaning we having a 4 hydrogen environment, 4 different hydrogen environment. Because of that, you can see 4 peaks here. Okay, 4 peaks here. And the chemical shift tell us the environment the hydrogen is in. Okay. So meaning, okay, in here, okay, so I mean if you start from TMS, okay, which is I think last week we discussed about why we choose TMS, okay, because it's appear at delta 0, okay, more or less is like our reference, and I think the signal is quite strong, and the rest actually is going to appear, I think maybe a few ppm away, from TMS, all right. So due to the environment that they are facing, okay, due to the environment that they are having, I mean, it's going to give them, a different shifting as well, different chemical shift. So today, inshallah, okay, we're going to discuss a bit about the chemical shift. Okay, so that's why, okay, because this 4 environment, this 400 environment, actually they having different environment experiencing different basically magnetic field. Okay, so that's why they appear at different values of shifting. All right. So similar here as well. Okay. So we have 2. And the integration trace tell us the number of hydrogen in the environment. So this actually, this number here, 1, 3, 1, 2, 2, 9. Okay, this actually the integration number. Okay. So sometimes, okay, if not given this number, you are given, the percentage. Okay. Okay, in the normally, the way we do it, either we know the integration like what been shown here. Okay, the number 1, 3, 1, 2, 2, 9, or maybe some other numbers. Okay, related to that particular what you call it, compounds. Okay. If that not given, okay, normally you are given, the abundance, okay, the percentage, okay, the percentage, and you are also given the number of proton, okay, available in that particular structure. Maybe they will give you, it's not the chemical formula, okay, the chemical structure, okay, and then from there, okay, you need to find out, the number of proton in each environment. Okay, I mean vice versa. You can do either the first one, okay, you are given, the what you call it, the integration, okay, trace, or second, okay, you are given, the chemical structure, the what you call it, the brief structure of the compound, and also, the abundance, so I mean both actually you can work out, okay, to know what, the number of proton available in that particular compound. Okay, see proton NMR splitting pattern videos for info on splitting. Okay, I mean actually he has a series of videos, so I just attest, I think it's about 3. Okay, the basic one. Okay, if you okay with the method, okay, that I mean the method, I mean the way he explained, okay, maybe you can just simply, okay, I mean visit YouTube and you will find, I mean the video is there. Okay. And secondly, he explained also, that, I mean, because most of the compound actually in solid. Okay, so we need a solvent. And solvent, if we use water containing hydrogen. If you are using water, dissolve your compound and then you run your sample, your NMR machine is going to detect both hydrogen from your compound as well as hydrogen from your solvent, which is water, for instance. Okay, so we don't want that to happen, because you're going to crack your head, so you don't know which is which. Okay, so to avoid that, basically, okay, we use solvent, okay, without having any hydrogen. So no hydrogen based solvent. Okay, So you can think of it. Okay, there's many options that you can use. Okay, one of them actually deuterated, okay, solvent. Okay, and also maybe carbon tetrachloride, okay, can be used as well. Okay, so similarly here, you know, the D2O shake, okay, they mentioned just now. Actually, normally we use this, okay, to confirm the presence of NH and OH, you know, in the what you call it, I mean in the compound, okay, by using proton NMR. Okay, simply because of the deuterium here will be able to replace, you know, hydrogen here. Okay, and that basically once you do that before and after D2O shake, okay, you should be able to tell, okay, the presence of OH group supposedly after you adding D2O shake. Okay, the spectrum here, you know, the spectrum is going to disappear. Okay, disappear, you know, from the spectrum. Okay, now that's more or less, okay, what he's saying. You know, to me this actually is very simple approach. This summarizes everything, okay, in in one page of lecture note. Right. Now I'm going to share, you know, the. Okay, I go on chemical shift first. Right. What chemical shift? Actually, I don't want to explain in detail. Okay. But as you can see from the explanation, okay, given, you know, I mean, shown in the video just now, different group of hydrogen is going to experience, okay, different environment. Okay, simply because of, you know, the electron environment is different. Okay. So all protons do not show resonance at the same frequency, okay, at the same shifting. I think we know that. Because they are surrounded by particular number of valence electrons, which vary from atom to atom, isn't it? Because I think the compounds very complicated. So basically, you know, each what you call it, each proton, okay, will experience different valence electron environment. Okay, so the valence electron, okay, of each hydrogen, okay, will experience different electric environments. That's cause, you know, why, okay, they're going to I mean have, you know, the chemical shift at different ppm values. All right. So positive signal in spectrum help us to know nature of proton. Okay, what I'm saying here under this basically sunatullah. Okay, so Allah has created that way. Okay, mana Allah has created, you know, I mean I mean the what you call it, the surrounding electrons. Okay, basically it's going to influence, you know, I mean the what you call it, you know, the nucleus, okay, in the proton, and as a result they're going to appear at different what you call it, delta values. All right. So position of signal in spectrum help us to know nature of protons. Okay, for instance, either whether the protons coming from aromatic group, whether they came from aliphatic, aromatic, actually the apa ni, benzene ring to aromatics, or maybe that's not necessarily benzene ring. Okay, some other ring also related. Aliphatic, you know, the long chain acetylenic, vanillic, additional releasing or withdrawing a group. So these are going to basically influence, you know, I mean the shifting, okay, the chemical shift, you know, of certain hydrogen. So does each proton absorb at different field strength? Okay, because each proton going to experience, you know, different what you call it, the electronic environment, and as a result, they're going to appear at different field strength. Right. This actually, for instance, another, you know, the shielding and deshielding, okay, the concept, okay, that's going to govern, you know, the chemical shift. So we are having here actually the unisolated proton. Okay, so see actually the isolated proton, meaning it's so far away, you know, from other electron environment. Okay, so meaning, I mean the nucleus is on its own. So since, I mean, you know, the proton is isolated, okay, so it's not going to experience, you know, the secondary magnetic field, okay, that might be generated, you know, by the electron surrounding. So as a result, okay, the nucleus of proton here is going to experience, you know, it's going to feel, you know, the B naught only, okay, I mean the magnetic field, you know, from the instrument only. All right. But for the second situation, okay, so we call this as deshielded, okay, no shielding or deshielded. Okay? But here, a proton surrounded by electron density. So we have a proton, okay, hydrogen proton, and surrounded, by electron density. Maybe, from the vanillic group, okay, maybe from the what you call it, from the benzene ring, okay, or maybe from the electronegative atom that attached to it, okay, for instance. So as a result of this electron, also is going to induce, magnetic field as well, okay, magnetic field induced by the electron, and normally it's going to opposite, the magnetic field that have been induced actually in opposite, okay, to be not here. So in a way, this secondary magnetic field is going to shield, okay? It's going to shield the nucleus here. So the induced field decrease, okay? The induced field decrease the strength of the magnetic field, okay, felt by the, because they have, their own shielding here. So, the nucleus is going to experience less B naught, okay? Okay, because they also having, the secondary magnetic field. So, the nucleus is going to experience less, okay? Magnetic field, from the magnet of the instrument. Okay. So actually, this slide also explaining the same thing. Okay, the cost of shielded and deshielded. So for shielded nucleus, okay, like what we have, okay, this is the shielded, non-shielded, shielded, okay, deshielded, shielded, deshielded. Okay, for the shielded nucleus is going to feel a smaller resultant field, okay, because of they have their own, okay. So what they are going to experience from the main one actually is less, all right. So a larger induced magnetic field, all right. Because here, for the shielded, nucleus is going to feel a smaller resultant field. So as a result, the difference here actually is big large. Okay, the secondary is large. So what's going to be experienced, by the nucleus from B naught or B alpha here actually is going to be larger. Sorry, going to be smaller. Jangan confusion there. Okay, for the shielded, okay, the shielded ni mana tidak ada elektron, maknanya elektron tu very less. So in fact the secondary magnetic field also is very small, very small. So the nucleus is going to feel a larger resultant field, from the magnet, okay, from the main magnetic field. All right. So I think for the shielded here, as the electron density around the nucleus increases, okay, for the shielded, as the electron density around the nucleus increases, the nucleus feel a smaller resultant magnetic field. So a lower frequency is needed to achieve resonance. Okay, mana dia experience smaller, okay, because they already having induced, on their own. So what they experience, from the main magnetic field actually is lower. But here, because of, for the deshielded, the electron density around the nucleus decreases a very small amount, and we expect, the magnetic field that been induced actually is very small or maybe negligible. As a result, they're going to experience, the larger, okay, magnetic field, okay, from the instrument. That was what we were trying to say. Okay, so still the same concept. Okay, I just detail it out. Okay, so that if you wrote on your own, okay, and then you will be able to understand. Okay, so right, so the basically summarizing. Okay, summarizing. The shielding effect. Okay, when shielding occur, and this actually the shielding scenarios. Okay, where basically the electron density surrounding the nucleus actually is less. Okay. So for the shielding effect, an electron shield the nucleus, the absorption shift upfield. Okay, so we can see, the proton here, and yet the proton plus electron. Okay, so it's going to move upfield. Okay, the shielding effect. Okay, because of electron. Okay, electron that present, from the environment. Okay, it's going to cause, the what you call it, the absorption. Okay, to move. Okay, to outfield. All right. But this shielding, because electron density is less, okay, so they are actually going to shift it downwards. Okay, so for instance here, okay, so we're having carbon tetra. Sorry, this we're having CS4. Okay, which is, sorry, bukan carbon tetrachloride. Ini actually, you know, the methane, okay, methane, and then once, okay, this is a chloroform, okay, we put, I mean, in chloroform, we're having one chlorine atom. Chlorine atom is going to, actually, is electron withdrawing, isn't it? Electron withdrawing. As a result, you know, I mean, the electron density, okay, in chloroform is basically much less, okay, compared to CH3, CH4. So as a result, you know, I mean, the de-shielding effect is going to occur, you know, and the absorption is going to shift, okay, downfield. Okay, so you can see. All right, so this as a summary, sorry, as a summary. We have shielding versus de-shielding. Okay, we're having downfield, we're having outfield. Once the increase, when the shielding increases, I think, you know, the pitch is going to move, okay, to downfield side, okay, to the left. You know, but if the shielding increasing, okay, I mean the what you call it, I mean the pitch is going to move, okay, outfield. Right. Remember why we choose TMS, okay, last time, okay, as a reference, simply because of low electronegativity and also, you know, the shielding of equivalent proton, okay, is going to give one very significant NMR signal that's going to appear, okay, at the right hand side, you know, and we can simply found, you know, the values of delta equal to 0 to TMS, okay. So assigning delta equal to 0 here, okay, for TMS. I think I already touched about this, okay, in our last lecture, Ananda. Okay, some factors, Ananda, that affecting chemical shift. I think by now we should be able to guess, okay. By now kita dah boleh agak dah, okay. A factor affecting chemical shift ni, okay, because of, you know, the electron environment, okay. I mean, what we need to consider whether the electron actually more electron, you know, available or less electron available. Okay, so the effect is either the pitch going to move outfield or going to move downfield. All right. Okay, so among others, electronegativity of the nearby atom, okay, simply like, you know, what we have shown just now. Mana tadi? Okay, here. Okay, for instance, you know, from the methane, okay, to chloroform. Okay, so I mean, chlorine is going to attract, you know, the electron and cause, you know, the electron, okay, experiencing, you know, by the proton actually is less, and that's why they move, okay, to a downfield. Okay. Right. So electronegativity of nearby atom is one of the factor. Hybridization of adjacent atom. Okay. So whether sp3, sp2, sp4, and so on. Okay. sp4 actually for saturated carbon. So sp2, okay, and sp, okay, you're talking about maybe the triple bond, maybe double bond, and so on. Okay. And we know, you know, for the unsaturated bond, okay, which is maybe sp2 or sp, okay, is containing electron that's going to move, okay, within the I mean the pi electron is going to move freely, okay, more or less, and that's, you know, we're going to basically influence, you know, the population of electron in there. As a result, okay, it's going to give, you know, different electron environment, okay, nearby that particular hydrogen atom. The magnetic effect, okay, from adjacent pi bond, I think by now you know what is that diamagnetic, okay. Basically, the electron, okay, is going to be paired, okay. Induced effect, okay, so any induction, okay, that may occur, van der Waals, okay, dishielding, okay. Anisotropic effect, we're going to see that later on, hydrogen bonding, and so on. So these are basically some factors that might affect, okay, the chemical shift of a proton. And you can see from here, I mean to see that, for instance, when we talk about electronegativity, okay. So we're having more or less, you know, CH3X, where X is actually basically, you know, the substitutes, okay, that might representing, you know, the atom or maybe a group of molecule with different electronegativity. You can see from here. Okay, fluorine, hydrox, OH minus, Cl, Br, I, and so on. So you can see, you know, that these are basically the electronegativity. Okay, so once we move from the top down, okay, actually the electronegativity is going to decrease, and as a result, okay, you can see, you know, that the chemical is also going to decrease. Okay. For instance, for a TMS, okay, we can simply assign 0, for the delta because this is our reference, okay. But the rest, once the electron negativity increase, okay, so I mean the population of the electron is going to be decreased as well. As a result, okay, that's why we notice that the chemistry also is going to increase once we move from bottom here and then to the top. All right. Okay, this explain again what I explained just now. Okay, so hybridization, okay, hybridization of adjacent atom. Okay, so we're having okay, this alkyl saturated. Okay, so sp3 more or less. Allylics, I did the sp2, and this sp. Okay, so you can see, that the difference, okay, in the chemical shift as well. All right. So again, okay, because of we're talking about the difference, pi electron here and pi electron here, that's going to move freely. As a result, it's going to influence, the distribution of the electron, okay, at that vicinity. Okay, diametric effect, okay, from the adjacent pi bonds, okay. So carbon-carbon triple bond shield and acetylene hydrogen and shift it to lower frequency, okay, to the smaller delta. So you can see from here another delta of H, okay, for instance, they attach, okay, to different, more or less it's like the same like what we discussed earlier, okay, but in this context, actually, we discuss in terms of, the diamagnetic effect, and you can see, the chemical shield also is different. Right. And then this is more specific, okay, for the benzene, okay, for instance, okay, benzene, as we know, I mean, it's having, the resonance structure, and it's quite unique, okay, because the electron is going to move freely within, the benzene ring, all right? So in the magnetic field, okay, the 6 pi electron in benzene circulate around the ring, creating the ring current, okay, you can see from here, okay, the ring current here, okay, I mean, these two are basically the same explanation, okay, but I'm putting both of them, okay, I mean to give a better understanding, okay, in case if maybe if you want to compare them, okay, but actually telling the same story. Okay, the magnetic field induced by the moving electron reinforce the applied magnetic field in the vicinity of the proton. Okay, so you can see from here. Alright, sekejap. Tak terlindung ya. Alright, actually, these are basically the applied field, the B naught, and here actually the induced magnetic field, okay, the field that been generated, okay, from the movement of the electron here, which is you can see in the same direction. This is B naught, okay, outwards. This is actually the induced magnetic field. So actually in the same direction, so it's going to reinforce. It's going to strengthen, okay, the applied magnetic field in the vicinity of the proton. Thus, the proton feel a stronger magnetic field and a higher frequency is needed for the resonance. Thus, they are de-shielded and absorbed downfield. Okay. So they shielded, meaning it seems that there is no magnetic field. Since the secondary magnetic field is not going against the be not okay the magnetic field, the magnetic field from the instrument, but instead they are reinforcing each other. So it seems like the net effect is like the benzene structures not having any electron presence. As a result, okay, it's considered de-shielded and it's going to absorb downfield. It's the same thing. That is for alkene. For alkene, just now we're talking about the benzene ring. Okay, so but for the alkene, so we're having more or less one unsaturated bond here. Okay, so we're having one sigma and also one pi bond. So the induced magnetic field reinforce the external field be not in the vicinity of the proton. The proton are shielded, the absorption is downfield. Right? So the effect is the same here. Okay, for the alkene, in this case, okay, we will notice that the pi electron of the carbon-carbon triple bond are induced to circulate, but in this case, the induced magnetic field oppose the applied magnetic field. Okay, so depending, basically, whether the circulation of the electron is going to give a secondary magnetic field that's going to go against, the direction of the the main magnetic field, or will go in parallel with it. Okay, either reinforcement or destruction. All right. So that's going to give, you know, the effect as well. So in this case, you know, for the alkene, it's going to go against, you know, but, you know, for the alkanes, you know, and also for the benzene, it seems to be reinforced, okay, to each other. All right. Okay, so you can see from here, okay, another. So if you compare the three that I mentioned just now, okay, we're talking about the benzene, we're talking about the alkene, we're talking about the apa ni, okay, the alkenes, okay. So sp2, you actually sp2 as well, but here actually in the benzene ring. So highly shielded, and shielded. Okay, so the chemical shift is governed by that. All right. So here actually the anisotropic shielding and de-shielding. Okay, so the same thing. The concept is the same. Okay, basically. Um, So you can see from here, field line oppose the applied field, creating a reduced field in the region. Okay, I mean the movement. So anisotropics, okay, in this magnetic field line, okay, due to the induced circulation of pi electron in the benzene field line. Actually, this actually slightly, actually in addition, okay, to what been discussed, okay, just now. All right, okay. So as a result, it is like what you can see from here. Okay, so we're having, like here we're having, you know, the benzene. Again, we're having, you know, some other carbon, okay, and attached, you know, to it actually the hydrogen. So here especially, you know, the positive and the negative, okay, explaining, you know, the movement, you know, of the electron, the circulation, and so on. That's finally going to give, you know, the magnetic field. Okay, that's going to, some of this going to oppose, okay, and the activity is going to go, it's the same person as the magnetic field. Okay. So just summarizing, okay, based on what's been explained here. Okay, so I don't want to highlight that, okay, twice. Right. So as a result, another, if you go the whole spectrum, okay, if you go the whole spectrum of the chemical shift, basically more or less like we can maps, okay, we can maps, you know, I mean the chemical shift, okay, together with the structure, the available, you know, in our compound, okay. Supposedly, if we are talking about saturated, okay, we're talking about saturated compound like what we have in TMS. Okay, TMS actually, you know, is appear here is zero delta chemical shift, and this is saturated. Hydrogen attached to saturated. What you call it? Saturated compound. And here, okay, hydrogen attached, okay, to the next carbon, which is going to have double bond. So this actually is called allylic carbon, allylic hydrogen, saturated hydrogen, allylic hydrogen. And here actually we're having what you call it, hydrogen atom which attached, okay, to the same carbon. I mean attached to a carbon, and similar carbon also having, you know, another halogen attached into it. Okay, so we know that, you know, the halogen here actually is very electronegative, so it's going to reduce, you know, the electron distribution here. I mean, it's going to reduce the population of electron here. So this is going to give different electron environment, okay, to H. So similarly, vinylic so different. Allylic and vinylic is different. Okay, so vinylic actually the same carbon. Okay, where, you know, the atom where the hydrogen attached is actually is unsaturated carbon, and it's aromatic like what we discussed earlier. So you can see, okay, I mean when you plot this, when you see this, you know, the difference chemical shift basically is going to give, okay, different chemical shift depending, you know, on the depending on which carbon, okay, that the hydrogen is going to attach. Okay, so we have, you know, this table, you know, if you like, if you arrange, okay, so more or less, um, you don't have, you know, to remember this. Okay, this actually easily you can find it in any reference book. Okay, when you do your experiment, okay, for instance, maybe your project, okay, for instance, you can just refer this, okay, from the table. So here basically, you know, different type of hydrogen, and, you know, the chemical shift that we expect, okay, is going to occur. All right. So similarly here as well, as I mentioned, normally you will take a few slides, but maybe the way they present it is different in order for you to understand better. Okay. So TMS here again, this is saturated. Okay, TMS here. Okay, saturated compound, and then the benzene ring will be having carbonyl and so on. So we are moving from outfield, okay, into downfield here. So similarly, okay. So this is another example. Okay. For instance, in this compound, okay, and the compound we're having two environment. Okay, we're having two environment. This is the first environment of hydrogen, which is the same, this symmetry. Ini dengan ini sama. Okay, so this the methyl group is the same. So we expect it's going to give two what you call it, two peaks, and we expect this peak is going to appear at longer, or it's going to appear downfield compared to the first one, simply because of the presence of chlorine atom. All right. So similarly here, okay, so we're having more or less 1, 2, 3, 4, okay, because we're having 4 different environment. One, the methyl group, H and H, because this is actually very close, to this, and this H actually directly attached, to the same carbon as, the carbonyl group. All right, so that's why we're having 1, 2, 3, 4, okay, different peaks, okay, corresponding to 4 different hydrogen environment that have been experienced, by, or I mean they're available, okay, in the same structure, in the same compound. Okay, that another for I mean we done that, okay, for the shifting. Okay? And now I'm going to move, okay, to the second slide. Sekejap ya. Start this one. Okay. Any question, Ananda? For the shifting, maybe it's a bit difficult. Okay. New concept. Okay, to you. Okay, before I proceed, okay, to the spin coupling.
Tak ada.
Alright. Okay, bagusnya. Ini mesti boleh follow dengan baik. Alright. Okay, so maybe I start. I continue, okay, with the spin splitting. This is very important. Okay, because from the spin splitting, you are able, okay, to determine, okay, how many carbon, how many hydrogen, how many atom of hydrogen atom that available, that cause, that splitting. And from the splitting, of the spectrum, okay, so you know the nature of the protons. This is actually considered also Sunatullah. Yeah. Okay, so basically, peaks are often split into multiple peaks due to magnetic interaction between non-equivalent proton on adjacent atom, or adjacent carbon. All right. So I think the principle. Okay. So peaks, as what we saw, just now from the previous slide. Okay. The splitting pattern, some of them is going to show only one single peak. Some of them going to show a doublet, okay, 2 peaks, okay, very close to each other. Some going to show, triplet and doublet, okay. So this depending, okay. So basically, what we're going to see, I mean the splitting as you do the magnetic interaction, okay, between non-equivalent proton on the adjacent carbon. So we have carbon attached to carbon. So I mean the hydrogen that attached to the first carbon, the splitting pattern is going to be going to be influenced, but whatever by the group, okay, that been attached, by the group that attached to the second carbon. What that I'm trying to say. So the process is called spin splitting or spin coupling, okay, because they're going to couple, okay, and actually they're going to split, okay. So spin splitting, it occurs only between non-equivalent proton, okay. So if that proton actually is the same proton, okay, so I mean splitting is not going to occur. Splitting only going to occur, okay, between, you know, the non-equivalent proton. Okay, we'll see, you know, for an example later on. Okay, on the same carbon or adjacent carbon. The peak could be doublet, triplet, quartet, multiplet, and so on. So depending on the proton, okay, that available is same carbon or the next carbon. A signal coupling and interaction in which the nuclear spin of adjacent atom influence each other, and this is the same thing, okay, the same statement. Splitting of NMR signal into a set of peaks by the influence of neighboring non-equivalent hydrogen. This is actually basically, you know, the what you call it, the definition. Signal coupling is the same thing basically. Interaction in which the nuclear spin of adjacent atom influence each other, and this include the splitting of NMR signal. Signal splitting of an NMR signal into a set of peak by influence of neighboring non-equivalent hydrogen. So basically referring to the same thing. Okay. These are the rules, okay, that you need to remember, Ananda. All right. Because you want to know, okay, how many splitting going to occur, whether this is going to split or not, okay, for instance. So these are basically some of the rules, okay, that will be followed, okay, that you need to know. So equivalent proton do not split each other. Ini sama tak? Okay, proton 1, 2, 3. Is this the same? So they, I mean, a carbon attached to a chlorine atom, and then this carbon attached to 3, okay. So this actually, kalau tengok this like pyramid, dia punya structure. So I think the distance is the same, only from each hydrogen, yeah, the distance is the same, you know, from the chlorine. So these 3 are the same, considered the same chemical. The CH3 proton are chemically equivalent, and therefore no splitting occurs. So similarly from here, because it's symmetry, right? Symmetry. So we expect, you know, these 4 CH proton, okay. Ini CH proton, okay, or proton that attached, you know, to C here, is all the same, and therefore no splitting. Okay, protons that are further than 2 carbon atoms apart do not split each other because jauh. Okay, so proton that are further than 2 carbon atom, okay, 1, 2. Okay, ini mungkin adalah, okay, ini splitting observe. Okay, splitting observe. Okay. But here, okay, so dah 1, 2, 3 carbon, okay, it's more than 2. So splitting not usually observed. Why we say not usually observed? Because sometimes it occur as well, okay. Depending, you know, on is there maybe any in between, okay, if there any you know, a group, okay, that been attached that's going to influence, you know, I mean the splitting. Okay, equivalent proton have same chemical shift without splitting occurs. Okay, so for instance here, okay, so we have one group of proton, okay, another environment of proton, and the third environment of proton. Okay, so each of them basically is different. Okay, because protons ini, okay, they are attached 1 carbon, 2nd carbon, 3rd carbon, so more than 2. So that's going to influence each other. So especially here, 1, 2, and 3. Okay, so that's going to influence each other. That's why this is going to appear as one single peaks. A CH2 P here is going to appear as one single peak. Similarly with C here, you know, the group C, the C group is going to appear as one single peak as well. No splitting, okay, because of each of them actually, you know, having the same hydrogen, same hydrogen, and the distance between, you know, the C hydrogen and the B hydrogen actually is quite far. It's more than 2 carbons. So similarly with B and A, okay, it's more than 2 carbons. Okay, now we're talking about a non-equivalent proton that's going to do the splitting. It's more interesting, okay, a bit challenging as well. All right. So HA and SP are on the same carbon. Okay, so this actually considered non-equivalent, okay, because normally we're having another functional group here, different functional group here. All right. H and B are on adjacent carbon. So non-equivalent proton can be on the same carbon and maybe on the adjacent carbon as well. All right. So if HA and SB are not equivalent, okay, the splitting is observed. Kalau the equivalent, okay, so tak adalah. Kalau not equivalent, okay, that's going to show the splitting. Non-equivalent proton on adjacent carbon have magnetic field that may align with or oppose the external field. Okay, meaning macam ni lah. Okay, so HA because HB, you know, if ini adalah different, if this considered as a different, of course lah, ni different lah, because it's different. HA and SB actually considered different proton. So I mean the magnetic field here, okay, the magnetic field here is going to influence, okay, the nucleus here. So similarly, HA, the electron here is going to influence, you know, the nucleus here. Okay? And the influence, I mean the resultant magnetic field could be in line or opposed. Okay, could be aligned or opposed, you know, the external field. All right. That's actually the reason why, you know, the splitting is going to occur, because different experience in terms of the magnetic field, different resultant, I mean, different magnetic field that's going to be experienced, you know, by the proton. Okay, it's going to give different signal. Okay, that's the cause of splitting. Okay, so this magnetic field, this magnetic coupling causes the proton to absorb slightly downfield when the external field is reinforced, or slightly outfield when the external field is opposed. Okay, jadi kalau cepusnya ni, okay, you imagine this, yang ni dia akan ada dua possibility. Okay, they're having two possibilities. One actually parallel and the other one actually opposed. Okay, parallel and opposed. So because these two possibilities, okay, so this is going to influence, okay, the nucleus here. As a result, the nucleus is going to experience two as well. Okay, the one that's opposed and the other one which is aligned with. All right. So all the possibilities here, okay, will cause the signal to split. Okay, we see that. Okay, so for instance, here, non-equivalent proton have different chemical shape in splitting occurs. All right, so we're having, okay, satu apa ni, proton here. This proton is going to be governed, okay, by these two, okay, by Hp, ada dua ni. Okay, so as a result, it's going to produce, you know, three peaks here. You know, the splitting occur and giving, you know, three peaks. And instead, you know, I mean, for Sp here, it's going to show two peaks, okay, because of, you know, the possibility influence, you know, by Ha. Okay, so Y3 and Y2, okay, we're going to see later. Okay, so splitting is not generally observed when protons separated by more than 3 sigma bond. Okay, so here, for instance, no splitting, okay, occur even though Ha and Sp is different proton. Ha and Sp different proton, but no splitting because of, you know, the distance actually. I mean, these two Ha and Sp have been separated by 4 sigma bond. Okay, 1, 2, 3, and 4. Similarly here, 1, 2, 3, and 4. Okay, so if more than 3, so no splitting. Okay, even though the hydrogen, okay, actually is different hydrogen. And how the doublet signal due to the CH2 group on Br CH3 occurs. Okay, all right. This actually you need to understand slowly. Okay, once you understand one of them, okay, suppose you understand the doublet signal, okay, you can understand the rest of it. Okay, listen. When placed in the applied field, which is B0, the adjacent proton, okay, we're talking about ni, okay, so remember ini adalah Br CH2 CHBr. So we're having two environment, the blue one and the pink one. Okay, the blue one and the purple one. Okay, so H here and H here is different. Okay, so now we're talking about the H, okay, the blue hydrogen. When placed in applied field, the adjacent proton, okay, the blue proton can be aligned with, okay, either parallel, okay, with B0 or against B0. Possibilities in it. Okay, so when we place this, okay, the adjacent proton, okay, when we put this, okay, the CH2, we consider CH2 here. Okay, we consider CH2. So when this molecule, okay, being placed, you know, in the NMR machine, okay, so we consider about the splitting of CH2. Okay, so CH2 actually adjacent to CH, which is, you know, the blue hydrogen. So the blue hydrogen, okay, here will have two possibilities, either against or opposed, isn't it? Because they are only having one proton. Okay, this proton is going to give, you know, the secondary magnetic field either inline or opposed. Okay, the B naught. Okay, so meaning there is two possibilities, isn't it? Those the absorbing CH2 proton feel two slightly different magnetic field. One slightly larger than B naught, okay, because of slightly larger because of, you know, parallel, and one slightly smaller than B naught because of opposing. Okay, so are the two possibilities. Okay, slightly higher B naught and slightly smaller B naught. Since the absorbing proton feel two different magnetic field, they absorb at two different frequencies in the NMR spectrum, thus splitting a single absorption into doublet. Okay, that's why, you know, it's going to appear as doublet. Okay, so you can see from here. And tadi, oh tak ada, mana tadi? Okay, right? Is it the one? Oh yeah, we're talking about the same molecule. Okay, that's why they appear doublet. Okay, they appear doublet here. Okay, they appear doublet. Because, you know, this SB here is going to be influenced, you know, by the nucleus from the proton A. And there's two possibilities, okay? Either opposed or either opposed or either aligned, okay? So that's why they appear two, okay? Right, okay, so here, the explanation is here. Okay, how doublet signal arise? Okay, so we're having two possibilities, okay? With one adjacent hash, two absorbing hash fill two different field. Okay, so they absorb at two different frequencies. Okay, that's why we're having, you know, the doublet here. Okay, so one actually which is opposed, you know, you can see the arrow here, opposed, the one actually which is parallel. All right. So similarly here as well. Okay, so you can see one actually, you know, the reinforced, and the other one is the opposed. Okay, so that's why it appear as a doublet. So similarly, you know, with the triplet, another with the triplet, okay, because of we having now we consider, you know, the absorbing hash here, okay, and now the adjacent we have two, and this two also is different. HA and SP actually is different. Okay? No, it's not different. We consider differently. Okay, we consider differently. So HO and SP can each be aligned with or against. You know, there is two possibilities for each. So HA oppose and align, SB oppose and align. Okay, so you can see here. Okay, basically we're having, you know, those absorbing proton field three slightly different magnetic field, one slightly larger than B naught, slightly larger. Okay, because they're parallel. One slightly smaller. Okay, parallel but downward, and opposing. Okay, opposing B naught, and one the same strength. Okay, maknanya one upward, one downward. All right. So we're having three possibilities. That's why it appears to be triplet. Okay. That's why it appears to be triplet. Okay. And actually the areas actually 1 into 2 into 2, 1. Okay. 1 to 2 to 1. All right. So when two protons meet each other, they are said to be coupled. All right. So it's actually the explanation. It's the same thing like what we explained, you know, previously for the doublet. And similarly like that for doublet and triplet signal, this, okay, when we summarize, you know, for this molecule just now, okay. So we're having triplet here, okay, for the CH, okay, because adjacent to two hydrogen here, okay. So three, what you call it, triplet. Here we will not notice, you know, the doublet. So triplet, okay, doublet for CH2. All right. And how quartet signal arise? So it's the same. It's the same discussion. It's the same, you know, statistical explanation like what I explained, you know, for the doublet and also for the triplet just now. Okay, so here, okay, because we having okay, here actually what happened, you know, just now for the spin coupling, okay, involving you know, two adjacent proton, and finally it's going to produce, you know, two different what you call it, doublet. Okay, and here actually we're having triplet. Okay, and here actually we're having what you call it, the quartet. All right, because of, you know, the difference. Okay, and then okay, if you can see from what been explained just now, more or less it's like, you know, here, just like here. Okay, here actually we're having mana structure. Okay, here kejap ya, dia cakap structure nampak jelas sikit. Alright, okay, here maybe. Okay, so the structure here, okay, the structure here. Actually, you know, for this carbon, okay, only for this hydrogen, it's going to produce a triplet, isn't it? It's going to produce triplet, okay, because of we're having two here, and it's we have, even though we're having, okay, we're having two hydrogen, but it's going to produce three peaks. So it's like two. I mean, the rule is like 2 + 1, isn't it? Okay, because two hydrogen plus one, so that's why they're going to produce three peaks. Okay. So similarly, you know, for I mean, mana tadi ya? Right. Okay. Similarly for here, okay, I mean for this carbon, for this sorry, for this hydrogen, okay, it's going to produce doublet. Okay, produce doublet simply because of the adjacent here we're having one proton. Okay, the proton here. So the proton here actually is one and then plus one. Okay, so number of protons is one, and then if we plus one, so that's why we're having two. So basically, you know, I mean, the rule just now, okay, try to simplify, okay, the things, okay, the rule, okay, is try to simplify, I mean, by introducing n+1 rule, okay. So, well, actually, we still dealing, you know, with the same, we are dealing still with the same, what you call it, with the same compound, okay. 112 that tribromomethane, tribromo18, which has two type of equivalent proton. Thus, it shows two peak in NMR spectrum. Okay, you can see, you know, from the previous slide. Okay, but the actual spectrum consists of two peaks, but subdivided into 3 and 2 such peak. Okay, subpeaks or splitting ones for CH and two for CH2P proton respectively. All right. So those phenomena of splitting of equivalent proton into n+1 rule, where n actually the number of equivalent proton attached to the adjacent carbon to the proton under consideration is attached. So as per the 1+1 rule, okay, in 112 tribromomethane, okay, the one that we consider as our example, the C1 has two equivalent proton of methylene on the carbon next to it. Therefore, the n equal to 2, and hence it will split into 2 + 1, so 3 becoming triplet. Alright, so macam ni anak dia. So maknanya n+1. Okay, n2 referring to the number of adjacent proton. So for this one, it appears to be 3 because the adjacent proton we having 2. So 2 + 1 so 3. That's why they appear 3. Okay, but here, you know, for HB, okay, it's going to give us, you know, the two peaks. Okay, it's going to give us a doublet. Why? Because the adjacent proton actually we have 1. So 1 + 1 is equivalent to 2. That's why doublet and that's why triplet. Okay, so n+1 rule we call it. Okay. So this is another example. Okay, you can see from here. You know, if you run, okay, CH3, Cl2, okay, these are more or less, you know, the spectrum that you can to have. You can see from here how many environment of hydrogen. Maybe we don't have much time again to discuss, but if you understand another, here we're having two environment of hydrogen, isn't it? One actually A here, CH3, the methyl, and the other one actually CH, which is B. So I mean for B, you can expect again because B is going to influence the proton B is going to influence by the number of proton in the adjacent carbon, okay, which is proton A. So since they're having 3 proton A, so we expect, you know, so n+1, so 3 + 1, so 4. That's why it's going to give quarter. Okay, 1, 2, 3, 4 here. Okay. So similarly for A, okay, for hydrogen A is going to be influenced, you know, by hydrogen adjacent, okay, to the next carbon, okay, which is only 1 proton here. So n+1, so n equivalent to 1, 1 + 1 is going to give you 2 here. Okay, so it's been explained here basically. You know, for this hydrogen, n equal to 1, this hydrogen. Okay, for this hydrogen, okay, n equal to 1. Okay, because here equal to 1, the signal is split into n+1. Okay, which is a 2. So that's why we're having doublet. So similarly here we're having a quarter. Okay. So you can see for another. Okay, supposedly these are, these are the typical questions that going to be asked in the exam. Okay, suppose the question asks you, okay, how to use NMR proton data to determine the structure. Okay, you are given here. Okay, so for example, the question asks, using its proton NMR spectrum, determine the structure of an unknown compound X that has molecular formula C4H8O2 and contain a carbonyl absorption in its IR spectrum. So the question already mentioned to you, confirming to you that, the compound having a carbonyl group, okay, and, the molecular formula is here, the brief formula, all right? So you are given here, okay, that actually this is a triplet, actually the quartet, and the other group, the other signal actually giving you a triplet. Okay, so and also singlet here. So we having three different hydrogen environment. So environment A, environment B, environment C. Okay, because three group of a signal. Okay, so we expect three different hydrogen environment. And here actually A producing triplet, okay, B producing quartet, and C producing singlet. So the adjacent atom, okay, the number of it, okay, you can expect based on what we discussed just now, okay. So in order for you to solve this problem, okay, so we're doing step by step, okay. So actually the example another that I'm supposed, okay, to explain it to you, okay, during your tutorial tomorrow. But actually the sample I put here already, okay, so you can have a look, okay, once you try, okay, to solve the problem, which related to NMR spectrum. Okay, determine the number of different kind of protons. Okay, we need to determine that. Okay, the number of NMR signal equal the number of different type of proton. Okay, we know that, isn't it? The number of NMR signal equal to the number of different type of proton. Okay, so but here what they're giving you basically, the integration. Okay, 15, okay, 11, and 14. All right. So this molecule has three NMR signal. Okay, that what I've been explained just now. Okay, A, B, and C. So three type of proton. And then step 2, use the integration data to determine the number of hydrogen atom giving rise to each signal. Okay, so total number of integration unit actually is given here. So total 40. And number of proton, because you are given here, the molecular formula. So we're having 8 proton, okay, here. Okay, so the 8 proton, and we're having, the 40 units, so divided by 8. So each unit, okay, is going to, each proton equivalent to 5 units per proton. Okay. And then you divide it, okay, you will get, that for signal A containing 3 proton, environment B, okay, giving 2 proton, and environment C, okay, giving 3 proton. So if the proton normally we can guess, 3 proton normally actually CH3, methyl, okay, and 2 proton normally CH2, okay, the one in the middle. Okay, here is 3, so we expect this could be CH3. So as simple as that, Ananda. Okay, so more or less, okay, you can do the arrangement, you can do the guessing, okay. And that's step 3. Use individual splitting pattern to determine what carbon atom are bonded to each other. Okay, so we start with the singlet. Okay, signal C is due to CH3 group with no adjacent non-equivalent H atom. Possible structure include why? Because of it's just single, isn't it? So single, so meaning there is no adjacent. Kalau dia ada adjacent tu, they must not be single. Kalau single tu, there is no other proton, okay, at the nearby carbon. So this could be some of the possibility, isn't it? Okay, so ada apa ni, could be methoxy, could be carbonyl, okay, could be saturated, okay. But actually it's been indicated, okay, that carbonyl group available, okay, I mean in the structure. So this could be, okay, but we don't know yet. Because signal A is triplet, there must be 2H, okay, on the adjacent carbon. So ini adalah sunatullah, Allah dah atur macam tu. Okay, so because ini triplet, so we expect mestilah based on the n+1 rule. So because triplet, so we know triplet actually n+1 equals to 3. So n equals to 2. Okay, so they must containing 2 carbon as 2 proton here, isn't it? And B is quartet. Okay, so quartet actually n+1 equal to 4. Okay, so n must be equal to 3. So the next adjacent carbon must have a 3 proton. Okay, and the information suggests that X has an ethyl group. Okay, so ini yang dicarankan lah. Okay, so actually based on this, okay, So, okay, based on this information, okay, basically you are able, okay, to determine the structure. So I don't want to go into detail and other. So I think better you go through into it because actually it's very simple, straightforward, okay, a step-by-step kind of guide, okay, that has been given to you, okay, so you can follow. Okay, I just want to highlight some of the, what you call it, the application of NMR spectrum. I think you know that normally we use it to identify the structural for inform isomers. And we have isomers, you can easily, okay, play around, okay, with NMR spectrum, okay, NMR proton spectrum, okay, to identify, okay, the structure of the isomers, and to detect the hydrogen bonding, okay, so we can determine that, okay, whether hydrogen bonding are really available or not, okay. Detection of aromaticity, okay, the aromatic group, okay, you know that, if aromatic present, it's going to appear at certain shifting, values, okay, certain delta values. Distinction between isomers and conformers, okay, cis-trans, okay, for instance, detection of electronegativity, okay, electronegative atoms or the electronegativity of certain group, detection of cell double bond character due to resonance and so on, okay. So there are some, of the example. So NMR proton information obtained from spectrum, number of signal, we explained already, integration of peaks, okay, we explained already, chemical shape, you know that, and splitting pattern, okay. So these are basically information that we can get, okay, from the NMR proton in order for us to elucidate, the structure of the compound, okay, that we are interested in. Actually, I'm now giving you some of the information that already been discussed earlier. Okay, the purpose of it, okay, basically to strengthen, your understanding, okay, and to avoid any confusion, okay, in your understanding. Okay, the atom is different environment, respond differently. Again, we discussed already. It's different environment. The proton produce signal, different position. Correct. Proton can be classified as equivalent proton and equivalent. You see what discussed earlier. Okay, this is an example. Equivalent proton semua sama. Non-equivalent proton is different. Okay, this could be, one group in another group. So maybe we're having two group of proton here. Okay. Right. Chemically equivalent proton. Replacing proton C1 and C3, C1 and C3. Okay. Give same compound. Okay. Contohnya 1-chloro-propane. Okay. So either you substitute at the first carbon, or at the third carbon is going to produce, the same thing. Okay. The same compound, which is 1-chloropropane. I think we know that. C1, C3 proton are chemically equivalent and have the same chemical shape. Okay, we expect that as well. Replacement of hydrogen give a unique diastromers, okay, with a second chirality center. All right. So I hope by now you know what is carbon chiral. Okay, chirality. What is chirality? I don't have time to explain that. Okay, because of this actually supposed to be covered in organic. Okay. But actually, basically, just Romans, okay, something to do, with the chirality, and this actually basically, okay, can be, I mean, the study can be done, okay, by using NMR proton as well, okay. So here, for instance, okay, so if we replace, okay, either H or H, green H, or the blue H, okay, with X, okay, X, okay, normally the halogen group, okay, is going to give two possible replacement product, and the two product are the diastromers, okay, and we can determine, okay, basically the difference, in the signal, okay, by using NMR. A chemically non-equivalent proton, equidistant proton can have different chemical shift. All right, so you can see from here, okay, for instance, okay, D5.3, D5 delta, D sample delta 5.5, okay, which is very close, okay, but it's different. Okay, proton are electrochemically equivalent but not identical. Okay, so we know that as well when we talk about inotropics. Okay, I think all the concepts actually have been introduced, in the organic chemistry. Okay, this also can be determined, okay, by using NMR proton, inotropics proton. Right, this is explained, okay, about inotropic protons. Okay, you can go later on, and then homotropic methyl group. This methyl are homotropic. They are related to, okay, because 100 degree. Okay, you can see from here. Okay, it's like mirror image. Okay, 180 degree. Okay, so basically it's giving you the same chemical shape. All right, diastropic, diastereo, okay, diastereotropic methyl groups. Okay. So this also going to give a different chemical shift. So you can see from here, basically, the NMR is quite, I guess, quite useful. Okay, I mean, with regard, to isomers. Okay, and something which is okay similar into it. Okay, so it can easily be used to differentiate. Right. Well, I skip this. This is actually some of the pattern. I mean, this is actually the MX pattern. Okay, so having this benzene ring, and then we're having three different type of what you call it, proton. Okay, so even though adjacent to each other, okay, but I mean the proton is different, and as a result, it's going to give a different signal as well. Okay. So this actually the what called AA prime XI pattern. Again, just actually this is an example of it. Okay. So similarly here. Okay. All right. So I go to this part. Okay, which is on integral. Peak areas proportional to hydrogen are in the. I mean, peak areas are proportional to the hydrogen in this signal. I mean, what trying to do. The signal that we have here. Okay, the peak areas. I mean, the areas of the peak under this signal actually proportional to the number of hydrogen atom, and it's going to give, I mean, it's given in a ratio. Okay, like what you saw just now. Okay, for instance, 1:1, or maybe 1:2, 9. Okay, for instance, depending on the structure. Okay, so we can integrate that, and then we can do. Okay, for instance, here, a chemical shift 1.2, which is belong to green peak, and 3.65 okay belong to the what do you call it? The pink, okay, or the purple peak here, and actually this the area. So 3 and this 1. Okay, so 1, 2, 3. Okay. So integrating the peak of two dimethyl propanoids in a stair step. So we call it this a stair step. Banner showed that there are 1:3 ratio corresponding to the ratio of number of proton. Okay, so in here, okay, because we know the structure two dimethyl propanoids, so we know that the number of proton actually is 12. So that ratio actually referring to 3 and 9. So similarly here, actually, so this is actually from what we discussed just now. Okay, we're having okay, CH3 here, which is all the same. Okay, and we're having here CH3, which is difference. Okay, so the ratio actually is 3:1. Okay, 3:1. Right. Similarly here, okay, we're having different ratio as well. Okay, so this could be yeah, actually representing the number of proton. Okay, and we're almost there. The proton NMR, proton NMR. Okay, we're talking about spin splitting. Okay, we already discussed that earlier. And let's say actually we are using the same here, the same example that been discussed okay earlier. So I just skip. Okay, but I mean he's giving extra information here. So you can go later on your own. Okay, so for instance, the multiplets. Okay, the digital multiplet here. Okay, you can have a look. Okay. And again, like what we discussed earlier, I think the slide is the same. Okay, so it's the same slide. Okay, I mean the same material. I guess the data slightly, presented differently. Okay, another example of it. Okay, para and meta. Okay, you can even differentiate between para and meta substitution. In some like each compound. Okay, like what we have here. Yeah, all the same apart from the meta and the para, the position of the chlorine atom. Okay, with regard to NO2 here. Okay, monosubstituted benzene ring. Okay, you can see the difference as well. So when you go through all this, the example is going to to help you to digest, the knowledge further. Okay, and you can see, okay, basically these users, I explained that before as well. Okay, that's about all. Another, I just want to show, very brief, on my own videos. Okay. So that actually basically, you know, on the carbon-13, the video actually is not that long. I think around about slightly more than 10 minutes.
Assalamualaikum warahmatullahi wabarakatuh.
This is
Okay,
me.
class. Today actually we're going to discuss, the final topic under the NMR spectroscopy, which is we're going to focus on the carbon-13 NMR. Basically, we know that carbon-13 is naturally occurring carbon
So
isotope.
the total
And,
length of this
like
video
other
is about 35 minutes.
nuclei, it is having,
So I
the
just
nucleus
going very
shape,
quickly. Okay, so
of
talking.
this compound.
Okay, I mean the same. Okay,
Or
so
story for,
pre-recorded.
okay,
So you can
of
just
the
go
carbon,
through it.
activated carbon. Right. I mean, from the previous table by electrons. Okay. So I mean the same applies, for carbon for each. Okay. So we have two. But if you look, at the carbon-13 spectrum. Okay. We have 1, 2, and 3 carbon, and the 3.
So another in here, basically, we're having the same compound. We're having the same compound, but we look at different NMR. Okay. The first one actually the proton NMR. Okay, and the second one actually the carbon NMR. So we compare together in order for us to determine. Okay, we use both. For the proton, actually we want to determine the position of the proton, and for the carbon, actually for the carbon-13, okay, we want to know the position of the carbon. In fact, you will find out later on, okay, that carbon-13 is much simpler, okay, compared to proton, okay, proton NMR. So here actually I
carbon,
compare.
Okay, you can easily okay, we can get, very useful information,
Real
for carbon.
comparisons.
NMR spectrum for 1-fluoropentane.
Comparison
Okay,
as well.
So
Okay.
we'll turn to on compound,
Some
okay,
example,
having
okay, for you to
more
go
absorption
through.
peaks, okay, because it's of them. But what we observe from the carbon, okay, that might been formed, from the reaction here. Okay, I mean.
Okay, another maybe I show one of the videos. Okay, that I think it's very good videos, and on the carbon-13. Okay, because today maybe I'm unable to cover carbon-13.
In this video, we're going to talk about carbon.
So this is the one I'm talking about. Okay, so it's a very nice video. In fact, the number of viewers also, I think enormous, a lot. I can't remember exactly. And the video actually is a bit long. Okay, around about 1.5 hours. That's why I have no time to share this with you. But I just said, so hopefully you're going to look on your own. Okay.
And A is the signal that appears approximately around.
Okay, so very
23.
example given here.
So keep that in mind. At chemicalbooks.com, they'll have those values. So that's going to correspond to the one that's higher. So that's the one with the chemical shift of 93. And the other one is 67. There's a drop in the chemical shift approximately about 10.
Okay, ada. So more or less, I think if you go through, my notes, okay, together with the notes, that I show you just now, I think you will have it's like more crystal clear, about the NMR carbon-13, okay, which is, as I said, is much simpler, okay, than a proton. Okay, so proton, I mean, by now, okay, I think you quite understand. Okay, but maybe you need to furnish a bit, okay, because especially when you never heard about this before, so you might want to take some time. Okay, normally in my case, I will spare my own time, okay, to really understand and go through the materials, okay, on my own, okay, on my own face, okay, on my own ikut time yang I sendiri convenience, alright. So the important actually for the NMR, okay, you need to know the concept of it. Okay, I mean that's based on the previous lecture, and then on the on the proton, okay, that we're having today on the chemical shift, what make it shift, okay, and then the trend in the splitting. Okay, you need to know that. Okay, kenapa dia split jadi apa ni triplet, okay, jadi singlet, okay, jadi quartet and so on. You need to know that. Okay. And then the same understanding that we have for the proton, the principle of it, okay, and also the splitting, okay, and also the shifting, the chemical shift, okay, will be used for the carbon-13, okay. So we're talking about the adjacent carbon, the possible, and I mean because actually in carbon-13 there is no splitting, okay. So actually the spectrum actually is much simpler, okay. But it's going to appear, at different, what you call it, chemical shift. The delta value actually is different, okay, depending, on the, of course, obviously hybridizations, I guess, going to influence, okay, in this case, okay, either sp3, sp2, or maybe sp. Okay, Ananda. So I'm going to stop there, okay. So again, for tomorrow, actually, I'm just going to share you, for the tutorial. I will not be around, but for example, that I'm sharing with you just now. Actually, that's the thing that I try to cover. Okay, I'm giving you maybe about a week, okay, for you to submit, your what you call it, for your tutorial, okay, together, with your colleagues, okay, with your what you call it, with your partners, okay. So we're going to use the same partners as what we use, for the practical. Okay. Is there any burning question they want to ask, Ananda? Are you okay, Ananda?
Okay.
Alila je okay lah, semua tak okay. Aswa, are you okay? Okay, Zahir dia kata good. Okay, tak tahu lah good tu apa. Okay. Okay, Ananda, if you have nothing, okay, to ask and nothing to discuss, okay, so it's my pleasure, okay, I mean, to be with you, for this course, okay. Looking forward, okay, to have you again, okay, to host you again in the near future. And I would like to take this opportunity to say good luck, okay, all the best, okay, for your final exam. All right. If you have anything, okay, you can just let me know. Okay. I mean the WhatsApp group is still there. Okay. In case if you think, okay, you want me to organize or maybe, okay, to arrange, okay, for kind of like discussion, okay, before your final exam, just let me know. Okay. Okay, ada kalau tak ada, okay, so we end the session, okay, by reciting tasbih kifarah, okay, dan juga surah Walas, subhanallah wa bihamdihi, subhanallah wa bihamdihi, asyhadu an la ilaha illallah, astaghfirullah wa atubu ilaih. So my regards, okay, to KSF2 students. I sure some of you are here. Okay, so for them